Okay, so today we have a smaller class for some reason. And okay, so today I decided to revisit the slides I did last time. So I was working on them today, clean them up a little bit and try to go over them one more time. Because I felt last time I didn't drive the point that I wanted to drive properly. So we discussed last time this basic idea of regression, which is the other side of curve fitting. So far, we studied interpolation, where you have well-behaved set of data points like the density and the temperature. There's like 1 point per independent variable, right? The data is kind of nice and well-behaved. You put an interpolant along those data. That interpolant goes through each and every point. So if you were to evaluate that interpolant at the input data, you'll get exactly the input data again, the y values from the input data. Regression, on the other hand, the other side of curve fitting says, okay, for most other data where there is observational error, where there is a lot of uncertainty, where there might be human behavior involved, where the science is not really exact, such as height versus femur, or for example, your budget, for example, over the years, however you're spending on your budget, like my ice cream budget, for example, like all over the place. It's been going up, since COVID, but things like that. The idea is not to capture the trend, to capture the data exactly, rather capture the trend of the data. And the idea is that if you capture the trend, you're capturing the science that tries to explain that trend. You'll get a formula for it, and that is usually quite helpful for doing predictions. Okay, so I illustrated this by taking a bunch of input data. I call them input data given by X and Y values, these blue dots over here. And we say, we want to capture the trend by putting a model curve along those data. Now, this curve doesn't have to be a straight line. Straight line regression is perhaps the most popular and the one that you've seen so far and that you do in Excel, but it is not the only one. And I hope once you're done with this class, you can do regression with like sines and cosines and logarithms and any sort of function you can dream of, okay? And we call the distance between those data points and the curve the errors. So I want to elaborate on that a little bit. And the idea for regression is to find this model curve that minimizes this distance between the model and the actual data, okay? It's easiest to do this on a straight line, and it's also easiest to do it with just a few points, okay? So I'm gonna take 3 data points, and last time we said you cannot fit a straight line, which has 2 unknowns, right? The slope and the intercept. You cannot fit it, you cannot drive it along 3 points unless the 3 points are aligned on a straight line, okay? Because you'll have more equations than there are unknowns. Okay, so instead we're gonna do regression. So I'm gonna take 3 points over here and again, call them the input data. And that input data, those input data are given as X values and Y values. So for the first point, X1, Y1, for the second point, X2, Y2, and for the third point, X3, Y3, they don't have to be ordered. Okay, regression doesn't care about that. And then suppose we want to capture the trend over here by this model curve. Now, I don't know where this line exactly is. It could be kind of sloped like this a little bit, sloped up. I'm just kind of drawing an illustrative straight line model to try to regress those data. And we'll understand again what we mean by regression doing that. Now, this model is given by the formula. We set the formula. We say we think those data, the trend for those data is best explained via a straight line. The formula for a straight line is A1x plus A0. We don't know A1, we don't know A0. That's our objective. Finding A0 and A1 so that we best fit those data. What we mean by best, we're going to discuss that. That's part of the discussion on regression, okay? Now, this model curve clearly you can evaluate that formula, A1x plus A0. We still don't know A0 and A1, but that doesn't matter. We can reverse engineering this. You can evaluate this curve at each one of those input data, right? So if you were to evaluate it at x1, okay, that will give you a value of f at x1. We call it f1. So essentially you say A1 x1 plus A0 is this value. Now we expect in general that this value predicted by the model is going to be different than the value y1 produced by the observation, because we're not doing interpolation. We're doing regression. We're trying to capture the trend. They might be on top of each other. They might be equal, f1 and y1, but that's not necessarily true. And that's okay. Okay, that's okay. That's part of our argument. And the same thing applies for x2. You get a prediction by this kind of red square. It's going to be different than the value you would have obtained from the observation. So remember, x values are independent variables. They're given to you. The y1, y2, etc., the y values are also given to you. They're the dependent observations. The f values are what your model is predicting at the input values. Now, why did we choose to evaluate the model at the input values? Because we know the input values. We know the input values, x values. We know the input y values as well. And we're going to use those information, or that information, to compute an error, okay? And based on that error, we're going to find the best line that minimizes that error. Okay, so let's continue driving this point home. I'm going to get rid of those lines. So now you agree that this y1 is really the y value observed, and this f1 is the y value predicted by the model. Okay, same thing for f2 and same thing for f3. The difference between these two is an error. Call it a true error or whatever. It's the difference between your prediction, your model prediction, and your actual observation, correct? You know this y1 is given to you. Eventually, we're going to find y1, f1. We don't know it yet. At this point, at this stage, we don't know it. But this is an error. It's a legitimate error. Same thing for all the other points. You have E2 and E3, okay? It's clear so far, I hope. Okay, so now in this case, we have these three errors. Now the idea is, okay, this line, we can do two things with it. We can change the slope, kind of make it kind of wiggle like this, or move it up and down, or do both, right? So you can run a Monte Carlo algorithm, which is essentially just randomly changing A0 and A1 and calculating the errors and finding A0 and A1 that minimize those errors, okay? Or we can do it in a more kind of deterministic way and actually derive the formula that minimizes the error. Now, how do we measure this error? We've learned, remember when we were doing iterative solvers, when we had a collection of errors for each unknown that you are solving for, we had an error, an iterative error, right? Or whatever, a true error, whatever you call it. And then we said all of those errors, we can aggregate them into a single number to represent that error. We use the Pythagorean norm. We're going to do the same thing here. We're going to take these three errors and combine them with a Pythagorean norm and define an aggregate error, a single number that represents those three errors. That would be E1 squared plus E2 squared plus E3 squared. If you had 1,000 points, you would have E1, E2, E3, E4, E1000, okay? Adding them all up. However, okay, so I think I'm missing a, okay, I think I'm missing a, sometimes my PDF, apologize. Let me quit my PDF viewer and restart it. It seems that sometimes my PDF viewer dies on me. So there should be an additional equation over here. Okay, one moment. It's not my fault. I'm switching. I used to use math type, and okay, there you go. There it is. Okay. So now we know that E1 is Y1 minus F1 or F1 minus Y1. It doesn't matter because we're squaring it, okay? And E2 is Y2 minus F2. E3 is Y3 minus F3. So that's our formula for the aggregate error. However, we know also the form of F1 and F2 and F3. It's A1xi plus A naught. F1, you just simply put xi, put x1 here. F2, you put x2, and F3, you put x3. Remember, F1 is the model prediction at x1. F2 is the model prediction at x2, and F3 is the model prediction at x3. And last Tuesday, we did an activity to fill in the blanks. You all did that, right? And this was the formula we obtained for the error. Why we call it S, I have no idea, okay? I wanted to call it E today, but then I looked at all the subsequent slides and some references, like everyone is using S, probably from Sir something from, you know, Britain or whatever. And so we're like, okay, let's just stick with S, okay? Call it sum of the errors, all right? Okay. So now we have a formula for the error, and that formula contains the two knobs, A0 and A1, that allow us to manipulate that line, right? So A0 and A1 allow us to either change the slope of the line like this, move it up and down, or do both, okay? And that representation of the error contains those two knobs. So now what we can do is find A0 and A1, or minimize that S, that error, that aggregate error, with respect, or find A0 and A1 that minimize S. So if you had a single valued function, f of x equals sine x, where does the extrema occur? Where do the extrema occur? It's when the derivative is equal to 0, right? You can get a minimum or a maximum. Over here, you have a two-dimensional function. And those two dimensions are A0 and A1, correct? And in multi-dimensional optimization, to find the extremum, so whether a minimum or a maximum, you just need to set the derivatives with respect to those two variables equal to 0. So in other words, S is minimum. So if you don't know this condition, learn it now. Okay. Same for a single valued function, f of x equals something. The extrema occur at f of x equals 0. Same thing for a multidimensional function. The derivatives must be equal to 0 with respect to the unknowns. Over here, A0 and A1 are the unknowns. Agreed? Okay. Now, I need to clarify something, and we're not going to delve into this, but for those of you who might be interested, we can have a separate discussion. This technically tells you where an extremum occurs. It could be a minimum or a maximum. And then to check if it's a minimum, you need to look at the second derivative. In higher dimensions, that's called the Hessian matrix, okay? Don't worry about that. Turns out that for all regression problems, this is always a minimum. If you satisfy these conditions, it's always a minimum. All right, no more math slides, okay? Okay, so now go ahead and do this. Go ahead and take this formula S and symbolically do these derivatives. Work in groups and remember this definition of the derivative, okay? So you're differentiating with respect to A0 and you're differentiating with respect to A1 and setting equal to 0. So get me those equations, all right? Who was that? Like, oh, who's always excited? I love that excitement. So to differentiate with respect to A0, you hold everything else constant, okay? Everything else is constant except A0. To differentiate with respect to A1, everything else is constant except A1, okay? start with the derivative with respect to a naught. It's a little easier. You might need to use this definition. The derivative of u to the power n prime is nu prime un minus 1. Jake, do you want to? You guys want to work together? It's okay. I know it's probably. If you can put your name tags in front of you, so I can know who you are when you have that excitement of yes, sir. Do it by hand. It will be a little bit more helpful for you. Kind of stuck. Okay, maybe I'll help you with a naught. Okay, I'll just take one term. Okay, so ds by dA naught, the first term. Okay, just the first term. If you take, so y1 minus a1 x1 minus a naught, that's your u to the power n. N is 2. Okay, so that gives you 2 times u prime. So that's the derivative of that quantity with respect to a naught. Y1 doesn't have a naught, so the derivative of y1 with respect to a naught is 0. The derivative of a1 x1 with respect to a naught is 0. The derivative of minus a naught with respect to a naught is minus 1. So you get 2 times minus 1 times u to the power n minus 1. So that's this entire quantity, y1 minus a1 x1 minus a naught to the power 2 minus 1. So that's to the power 1. Okay, so you get y1 minus a1 x1 minus a naught. Okay, now do the same thing with respect to a1. With respect to a1, you're going to carry an x1. So that's only the first term with for the first derivative. Okay, doing like some extreme algebra over there. Taking out. All right. You guys got it? Okay. You got it? Okay. Kind of want to work independently. Yeah. No, it's a 2 times. Yeah, that's 2 in the over there. Maybe my font is bad. I haven't written on a board since like technology was invented. I'm like, how do you write? Okay. All right, let's see. Who wants to do the first one? Just kind of spell it out. Who wants to do the first one? Some groups are still working. Okay, I'm going to randomly pick a group. You just had eye contact with me, so you guys have something? Yeah, do you want to do the first one? Okay, yeah, go ahead and say it. Yep. Uh-huh. Uh-huh. Okay. Okay. Mm-hmm. Perfect. And it just kind of follows this strategy. Now, what about A1? Isabel and Kara, do you have an answer? You're still working on it. Okay. Go ahead. Uh-huh. Correct. Yeah, you just have an extra X multiplying all of them. Okay. So this is the answer. Okay. So with respect to A0, we kind of did it on the board. With respect to A1, well, when you differentiate this quantity with respect to A1, you're essentially going term by term. dy1 by dA1 is 0. dA1x1, d minus A1x1 by dA1 is minus x1. So you get the minus x1. And dA0 by dA1 is 0. Okay. So you get this minus 2x1. And this is the whole quantity to the power n minus 1. The rest is essentially identical. Okay. So what's happened now is that I claim, when you look at this, this is the system we need to solve to obtain A0 and A1 such that S is minimum. Because we agreed that if we satisfy the conditions, ds by dA0 equals 0, ds by dA1 equals 0, that will give us, that will minimize S. And so happens when you carry all of this out, you get two equations with two unknowns for A1 and A0. Everything in red is unknown, everything is black is known, in black is known. Okay? So you get two equations, two unknowns. That's exactly what we're looking for. Now, before we plot this, we're going to do it for more than 3 points. We're going to do it for n points. Okay? And then see the formula and kind of just apply it and see how that works. But you see how we went from a problem where we had only two unknowns, A1 and A0, but more equations than there are unknowns because we had 3 points. Okay? So we couldn't fit a line just with those two unknowns at 3 points. So the methodology of minimizing the error is quite smart because, I don't know why it sounded like that. It's quite smart. I need some water, and the stupid water fountain out there has been shut down. So it's quite smart. It minimizes it results in two equations and two unknowns, which is exactly what we wanted from the beginning. And this is the same thing now for an arbitrary number of points. All right. So you're gonna get ready to do some more activities now. We're gonna take more points now. You know, cool, they drop kind of from heaven. And then you got x1, y1, x2, y2, x3, y3, you got etc. all the way to xn, yn. Could be 1 billion points, 17 points, okay? Doesn't matter, n points, all right? And now we're gonna put in this model curve, so kind of the same idea. That model curve, we decide the form. We say this model curve looks like A0x plus A1, A1x plus A0. And again, this model curve makes a prediction at each one of those x values. So at x1, it gives us a prediction f1, x2 gives us a prediction of f2. We don't know what that prediction is, but kind of we're reverse engineering it, okay? Same thing, f3, and so on, all the way to fn. And each pair defines an error, E1, E2, E3, E4, etc., all the way to En, okay? So you have n values for the aggregate error, E1 squared plus E2 squared plus E3 squared, all the way to En, correct? Just exactly like we did before, except now you have n terms. Okay, now this is actually going to be easier than the previous example because we're just going to use summations. Now, when you substitute the form for E, that's y1 minus f1 or f1 minus y1, it doesn't matter, then you can nicely write this as a summation over all the points. Summation of yi minus fi squared for I going from 1 to n, okay? Just write it as a summation. You don't even need to put the index on it, okay? Because implicitly we understand we have n points. We implicitly understand we got to carry the summation over all points. Now, exactly like we did before, we know the model form of fi. I want to use that word over and over again. I want you to use it. That model form, the model curve, that's your model, okay? You choose what it is. That's where your intuition comes in. And in this case, our model curve is a straight line, A1 xi plus A naught. So if we take this Fi and put it in here, you get this compact formula for the total error, okay, as a function of A1 and A naught. Now we apply the same idea. Find A naught and A1 that minimize the total error. And again, the same conditions are true. We might have 1,000 terms in that error summation, but there are only two unknowns, A1 and A naught. And to minimize that error with respect to those two unknowns, A1 and A naught, you have to satisfy those conditions. Well, to find the extremum, but we know this is going to be minimum because this is regression, etc. So we agree to that. Now I want you to go ahead and do this for this summation. You did it for like 3 terms previously. Now I want you to do it for the summation and keep everything in summation form. It's so much easier. Okay? Come on, get going. So what you do, remove the summation, do the differentiation, and then put a summation in front of it, and that's it. That's all you got to do. It's easier than the previous one. Students against numerical methods. Way easier, right? Yeah, you just do one term and then put the summation on. Rich, you got it, or you kind of still absorbing it? All right. No, so this it's but differentiate entire with respect to one you not. Okay.
You just put a sum in front of this and just like yi.
Yes, exactly. It's easier than the previous one. Okay. Okay. All right, who's got it? Who's gonna help us do this time? Students against numerical methods. Do you have an answer? You think so? You want to do the first one? Sum. Uh-huh. Uh-huh. Okay, yx1. xi. Yes. Excellent. All right, who wants to take the second one? Good. Yes. Times the sum. Yep. It's kind of easier, right? You just do it for what's in the parentheses and just put the sum on top in front of it. Okay. This is it. Very compact form. Okay. Okay. Now, if you can't see it yet, these are 2 equations with 2 unknowns because I have 2 red terms, right? And 2 equations. To see the system of equations, I'm obsessed with systems of equations. I want to turn everything into system of equations, and we're going to do the same here. Okay. So I claim that this is actually a system of equations. You can't see it yet, just multiply things out into the summation. So let's go ahead and do that. Okay. We split the summation for simplicity. Okay, so, and you can eliminate the -2, right? Because you have 0 on the right-hand side. So you don't need that -2 anymore. And just kind of split the summation out. You get sum yi and then minus a1 sum xi. Notice I can take the a1 out, okay? Because a1 is a constant, sum xi. But here I left sum a naught because you're adding a naught n times. So this really should be a naught times n. That's why I left it under the summation, because it's a naught sum 1 n times. Okay, and you see how that works out. Same thing for the one at the bottom, sum xi yi minus a1 sum xi squared minus a naught sum xi. Okay, now again, I think this form is not very clean. I really like the matrix form, but notice that this sum a naught is a naught times n, because you have n terms and each term has an a naught. And when you factor that out, it's going to be a naught times 1 plus 1 plus 1 plus 1 n times. Okay, n is the total number of data points that you've got. Okay, now go ahead and write this system of equations, these two equations and two unknowns, in matrix form. Okay, I've always said, when you look at equations like this, they're ugly. The matrix form is cleaner, more elegant, and sheds more insight. Okay, so go ahead and write this in matrix form. Coefficient matrix times vector of unknowns equal to a right-hand side. What is your name? Pardon. Okay, Marla. Okay. If you want to put a name sheet, please. Coefficient matrix times vector of unknowns, which are in red. You don't have to write them in red on your sheet. Equals to a right-hand side. All right. Okay. David, Maxime, you get something in the back? You wanna share? Go ahead. So first row, let's say first row is okay. Sum of xi, yi. Excellent. Excellent. Exactly. So this is it. Now you might not see structure yet, but boy, you're going to see structure once we start going to higher order polynomials. Okay. It's interesting, if you look at it row wise, you have n some xi, and then some xi goes here, and then some xi squared. Okay, and over here you have some yi, and then you multiply by xi. And I kind of see a pattern already. If we want to add one more term, do a parabola, for example, then I'm going to see n some xi squared, some xi squared, some xi cubed, some xi squared, some xi cubed, some xi to the 4, and so on. And that's the exact pattern that we're going to see. That's why this matrix form is very useful. Okay. All right. So now we got this. We can simply invert this system and find the solution. Now I'm giving you the exact answer over here because for straight line regression, it's kind of in compact form. It's a lot of summations, but it's very easy to get the formulas for A1 and A0 for any set of data points. Doesn't matter what xi and what yi are. And if, again, you're on an airplane and you're kind of wanting to do some calculations by hand, you would use this formula, okay? You would use this formula. And this is exactly what I did here, but I did it in a table. So I calculated sum of xi, sum of yi, sum of xi squared, and sum of xi yi, and I plugged them in over there. And I got those coefficients for the model prediction for the height versus femur. Remember, our formula was x plus 123.2 to predict a person's height based on the height, the length of their femur, which was x. So this is for the height versus femur data. Okay. Now, programmatically, and I forgot my tape measure. Next time, I'll bring the tape measure and we'll do some femur measurements and see if we get our heights correctly. But this is pretty powerful, okay? And in practice, I would not recommend at all that you program these guys. Nah, don't program these guys as is. Instead, we're gonna learn to program the coefficient matrix. And in fact, we're gonna come up with a strategy to build that coefficient matrix for arbitrary models. And then just find the answer, the coefficients for those arbitrary models, okay? So this is given to you more of a, you know, just out of rigor and closure, and you can know that this is what the coefficients look like. But really what I care about is that system of equations up there, okay? Because that is more generic, more powerful than just a specific answer over here, okay? All right, so now let's do some Python activity. And okay, I said here, instead of programming, it's preferable to program the system of equations and use Python to solve for the coefficients, okay? All right, so how do we do this? It's funny, in this chapter, we're gonna go through hoops and loops, and in the end, we're gonna learn a super easy technique, okay, to do all of this. But I have to guide you through all of this complexity and annoyance now, because to get to that point of using what we call the normal equations, is gonna take us some maturity of kind of seeing these things over and over again. So given a set of data xi and yi, how do you program this in Python? Okay, how do you put this matrix in? How do you put the entries over here? It's pretty simple, okay? N is simply len of xi. That's the length of your array. Could be a NumPy array, could be a list, okay, however you're loading it up. My guess is that if you're loading it up from a data file, it's probably gonna be a NumPy data or some pandas, okay? So you can get the length from that. Here, we're just working with lists and NumPy arrays, okay? But this length just gets the length of that array. So that gives you n. That's the first entry in the matrix, so upper left, okay? Then sum xi is simply numpy.sumxi. Can be easier, okay? So here, I'm assuming NumPy arrays, all right? What about sum xi squared? np.sum xi squared. That's pretty nice. And then all you have to do, so now we have xi squared. Sum yi is np.sum yi. And the last one, sum xiyi is np.sum xiyi. So it takes them, multiplies them element-wise, and sums them up. So now we have all the ingredients to build the array. And this is a simple example for the height versus femur data. For the femur versus height data, we're gonna work this example together in a minute. But you can see here how I'm building the NumPy array as based on the lists and np.sum xi, np.sum xi, np.sum xi squared, and the right-hand side b, I'm building it as sum yi and sum xiyi. And then I'm not gonna use an iterative solver or any of that. I'm gonna forget all of that. I'm just going to use numpy.linalgebra.solve because it's a small system. It's 2 by 2, right? Just use the built-in solver, and this is where I solve it. Sol equal numpy.linalgebra.solve a comma b. Okay, so what's next? What does sol give us? Gives us the soul of the regression line, but what does it contain? Sol, this variable contains a solution, contains something. What is it? Correct. It contains A0 and A1 in the order we programmed this array. If you had programmed it transpose, it would be A1, A0. But in this case, this is going to give us sol contains A0 and A1. Okay, so now we have A0 and A1 that find the line that minimizes the error between those data points given to us, xi and yi. What do we do next? How can we make a prediction? You need to program in a straight line, a0 plus a1x. So you simply write a little subroutine. So you grab a0, which is the first entry in sol, and a1, which is the second entry. And then you simply define a subroutine, y model, that takes an x value and simply program a straight line, a0 plus a1x. And you pass it an x value and make a prediction. Okay? So it takes 2 steps, right? Okay? Now, go ahead and grab regression activity 1 height versus femur notebook from the modules, and we'll work on this together. Okay. Actually, for these notebooks, I had a lot of time, and I was, I typeset discussions. It's very complete. Okay. So this is the first example for we're dealing with was our xi independent variables were the femur length and the height given to us. Okay. This is actually a subset from a larger population data set. And first we get the boilerplate out of the way. Okay, matplotlib inline, SVG, etc. And now I place the data points, the input data in NumPy arrays. Okay, if you are still loading up your notebooks, raise your hand. I can slow down. Okay. Once you got it, okay. Hannah, let me know when you get it. All right, let's go again. So you can start by executing this boilerplate cell. Really what you do, you should have like this, placed like in a text file on your desktop. And whenever you create a notebook, just copy and paste these few lines because they're like pretty much in 99% of all your Jupyter notebooks, okay? And this cell over here brings in the back, can you see? You want me to zoom in a little bit? Okay, great, thanks. So in this cell, I put in the xi data and the yi data into NumPy arrays, okay? Those could be loaded. Assume that that's given to you, okay? Now, the first thing, so there are 2 things, always remember, if you take anything from this class is 2 things. If you're in doubt, print it out. When you have data, plot it. First thing you do with data, just plot it. Get familiar with it, flirt with the data, understand it, learn about it, okay? So that's what we're gonna do. We're gonna plot these data. And I always prefer scatter plots. Because if you were to do a line plot over here, it's gonna be very ugly. Because this data realistically is just a scatter data, okay? So don't connect it with a line, right? This is what we'd expect. On the x-axis, the femur length. On the y-axis, the person's height. And for a given femur length, you might get 2 data points. And that's okay. Because humans are different, okay? And you get a range, you get a spectrum, okay? All right. Now regression to a straight line. Here we want to regress. This is the matrix. This is what we did. We've been doing for like an hour. All right, so let's go ahead and build the coefficient matrix over here. So now remember, in the slide, if you have your slides in front of you, remember that, okay, sum xi is numpy.sum xi, right? And sum xi squared, numpy.sum xi squared. And same thing, yi, xi, yi. So just fill in the blanks to build this matrix, okay? Tell me if you are having any issues. Right now is the time. You guys are always good. You got it. Your screen is like, it's impossible to see unless you're like perpendicular to it. That's cool. Very nice privacy. Like with my Mac, it's like you can see it from a mile away. If you're standing here, it's like, it's really, oh yeah, and see that all that. In the past, they used to have these like you'd buy like this bulky thing, you put it on top of your screen for privacy, and you see them on airplanes. Yeah. And it's like it's a hazard. If it breaks, it would kill you. It's got like all of, it's all glass, This is probably a relic. You can find one at Deseret maybe. Okay, let's see. Who's got this going? Okay. You want to help me? So what am I going to put in this first question mark? I put n. Okay. This one over here, mp.sum xi. And I kind of named them xi and yi for, simplicity. mp.sum xi and np.sum xi squared. Print a. Great looking matrix. Okay. All right, next we build the right-hand side. And don't worry if it's a column vector or a row vector or that. We saw that when we were doing iterative solvers, linear solvers. Python just works, okay? It just makes it work. It figures out how it needs to put these arrays, okay? All right, so for bi, mp.sum yi, and then np.sum xi times yi, and that's b, also looking good to me. All right, so finally we solve now. We have a and b. We put in our solution, numpy.linalgebra.solve. Remember, it takes coefficient matrix A and the right-hand side B, AB. And then I print my solution, and I get 123.207 and 1.004, right? So that's exactly what we had on the slides, which I did by hand, right? Now, these guys are A0 and A1, okay? So now the next step is to build a routine that implements our model curve. Okay, some of you are still typing, or are you all with me? Okay, great. All right, so next step is to build the model. So first we're gonna grab the coefficients. So sol is an array, right? The first entry is A0 and the second entry is A1. Now we're gonna take those A0 and A1 and make a straight line function. And I call it, y model over here. What does it take? It just takes a single argument, because I'm gonna bake in those A1 and A0. I'm gonna hard code them right here. You can pass A0 and A1 to a model. So if you want to generalize, let's say you have a different set of data, you get a different A0 and A1. It's up to you. I don't care. But at a minimum, this y model function subroutine needs an x value to make a prediction. That x value over here is the femur length, okay? So we return A0 plus A1 times x. Ta-da. Okay, so now we are ready to make a prediction. And in the example with bones that I gave last week, the femur length was 42 centimeters. So units are conserved here, okay? We're assuming all units are consistent with each other. So you put 42, gives you a person's height of 165.4 centimeters. Okay, so now, how do you see that regression line? You just need to plot it versus a lot of x values, or as a function of the input values. Doesn't matter, still gonna be a straight line. So this is what I'm doing here. I'm plotting my xi data, which were my input data, input x values, and I'm applying my model prediction on those x values. So this is gonna give me the straight line. This over here is the original plot, okay? And the rest are just formatting. Ta-da. Gorgeous. So what this entire system of equations did, kind of try to move this line, change the slope, move it up and down, change the intercept, both, to find the position of this line between those points such that the sum of the square of the distances is a minimum. No other line is going to give you a better fit. Okay, this is a unique solution. Okay. Okay. All right. Okay, let's go. I'll give you a break once we hit standard deviation. Okay, but we're not there yet. I want to talk a little bit more about other things. Okay. Could this be easier? Yeah. So now we know the mechanics of building that system of equations. And trust me, we're going to need it once we go unconventional for regression. But for standard regression, like straight line or a parabola, as we will see, a cubic, etc., you can also use polyfit. Remember, in polyfit, we said, okay, you give it xi, yi, degree, and gives you coefficients of a polynomial. But for interpolation, for n plus 1 points, if degree is equal to n, you get an interpolation. But remember what I said, and this is just a slide grabbed from the previous chapter. If you choose a degree less than n, then regression will be performed. So over here, you could have 1,000 points, which would mean a polynomial of order 999 if you were to do interpolation. But if you want to do regression to a straight line, you set degree equal 1. It will do a regression for you using methods that we already know how to use. Polyfit, okay? So remember, polyfit goes in 2 steps, and you can just finishing up your homework. Polyfit goes in 2 steps. You first calculate the coefficients of the polynomials, and then you evaluate. To compare to what we just did, polyfit, I swear COVID changed my pitch. I think that's what's happening. So polyfit is the equivalent, if you put degree equal 1, polyfit, I claim, is the equivalent of solving that system of equations that we just solved together. And we can prove this by looking at what is contained in P. Remember, P returns the coefficients of that polynomial. Exactly what our solution did when we inverted the system. Agreed? Now, my hypothesis, and I claim that polyval, which evaluates a given polynomial at a given value, is the equivalent of defining our y underscore model. Okay, so let's try this out. Open up your notebooks again. And there's no gap over here because I thought of this on my way to class. Okay, so we're going to do this together. Okay, using polyfit. Oops. So we can use NumPy's polyfit to perform regression in general. For regression to a straight line, set degree equal to 1. Okay. All right. So I'm going to say coefs or P or whatever you want to call it. NumPy dot, what was it? Where did we grab polyfit? See? Okay, NumPy dot polyfit. So maybe we just import them. From NumPy import polyfit and polyval. Okay. And then we do coefs is equal polyfit. Okay, now with polyfit, for some reason it's not doing a suggestion. So remember, polyfit takes xi, yi, and degree. So polyfit xi, yi, and for degree, I'm going to put 1. Okay? Print coefs. Now we should get, my hypothesis that we're going to get these two values. They might be in reverse order because polyfit computes the highest order coefficient first. Okay. Let's see. Did you run it? Look at that. Love it. 1.004, 123.2. Exactly to the decimal point. Because it's solving the same system of equations. Okay. Now, to evaluate that polynomial or that model, you pass it to polyval, you give it the coefficients, coefs, and you give it the value x, which is 42, and you get 165.38, which is exactly what we got here. Very nice. Okay, now you might be saying, oh, Professor Saad, why did you have us go through all of this? It's gonna get worse. I'm gonna get you through worse matrices, but then you'll see the light at the end of the tunnel that Python cannot do arbitrarily complex regression. You can, and I'll teach you how to program that, okay? That's why we need to start kind of getting our hands warmed up with building matrices like this, okay? So polyfit and the built-in interpolants, they just do an interpolation to a regression to a polynomial of a standard form. Once you break that form, you have to do it yourself, okay? All right. Now, one last comment, and then I'll give you a break, and then we will start the discussion on errors, okay? Okay. So last time, Nathan, I remember, you gave me that idea last time, and I thought, maybe it's a good idea to discuss this. So remember what you did last time when we had A0 plus A1x and 3 data points or 50 data points. You applied it at each data point, correct? So that's what we did with regression. With regression, we took the model, which is A1x plus A0, and applied it at each data point, okay? So y1 is A1x1 plus A0, y2 is A1x2 plus A0, y3 is A1x3, correct? Now, clearly, there's more equations than unknowns. This system is insolvable, okay? You have many more equations than there are unknowns. However, observe this. If I write this in matrix form, again, this is what you did last time and kind of inspired me to start this discussion about this here. By the end of this chapter, you're going to learn that this matrix is so special, It's going to simplify a lot of work for us, but you'll learn that later. But I kind of just want to show you a little observation over here. So call this matrix A. Okay, so you agree first that, again, there's power in writing things as matrix vector form, okay? So you agree that this is equivalent to this system of equations. So first row, 1 times A0 plus x1 times A1 equal y1. Then 1 times x1 times A0 plus x2 A1 equal y2. So that is equivalent to this. N by 2 times 2 by 1 gives you n by 1 equal n by 1. Okay, so this is a consistent system of equations, matrices. Call this A. And now what I want you to do is multiply this whole system by A transpose. So this is A, and this is A transpose. You just flip the rows and the columns, okay? So go ahead and do this multiplication by hand right now. So this would be this row vector times this column vector. That's the first entry. This row vector times this column vector. That's the second entry. Go ahead and do it. And once you get to an answer, I want you to say aha or eureka or something nerdy like that. Okay. I have 2 Nathans here, so always forget. Why didn't you say aha? I want you to say aha so that you can stand up and tell us.
Now I have a question. Like, how do you even get this matrix of like one's on the left side and other very
So think about it. What did we do to get this matrix? We took the model curve, A1x plus A0, and applied it at each data point. That's it, right? There's the aha. Okay, okay. So maybe let's give your colleagues an aha. Okay. Come on, try to do it. Well, keep going. So this should be okay. So think about this. This is 2 by n, 2 by n, and n by 2 should give you a 2 by 2 matrix. The entries, you take the dot products of this row vector times this column vector, row vector, column vector. Okay. So we had a huge aha over there with Maxime. Do we have another aha over here? Yeah, there's an aha. Yeah, yeah, right? Isn't this cool? It's pretty cool. Yeah, and that matrix, that little matrix over there, all it is applying the model curve at the data points. There's no minimization, there's no differentiation. Correct, you got it? Yeah. Yeah, so when you carry out the multiplication, you need to carry out the multiplication. Yeah, when you carry it out, you get 1, 1, 1, 1, and 1, 1, you get n, right? Yeah, you got it. Okay. So most of you had an aha moment in their heart. I really appreciate that. Okay, so when you carry out this multiplication with the A transpose, you get exactly the same system of equations we spent an hour deriving. Okay, because to be frank, to derive, to show you, to prove to you that this is equivalent to the minimization problem, it's probably going to take 2 weeks. At the end of your slides, if you look at the PDF, I have that proof over there. Okay, this is just a preview of what's called the normal equations method, where you don't have to do any of that complex minimization. All you do, you take your model curve, apply it at the data points to get A, and that's it. You multiply by A transpose, and you get your governing system of equations. That's the method that we're going to use by the end of the chapter. This is only a preview. I want you to keep that in mind, okay? Okay, now you can take 5 or 3 minutes. All right, take a breather and we'll discuss error analysis when we are back, okay? Zoom recording. Okay, guys. All right, I know you love talking, etc. Let's just bear with me a few more minutes and we'll be done, okay? All right, so we're gonna take a little detour now to understand how well these regression curves, right now we know how to do a line. You might know how to do others in Excel or whatnot, but now we know how to do a line. We want to understand how we can assess the goodness of a regression. How well does it do? Does it do a good job at all? Okay, so sometimes a regression doesn't do a good job at all because you might have used the wrong model or the data is not regressible at all. Okay, so I call this section of the chapter error analysis. And I'm gonna go back over some concepts that you've probably studied in statistics, etc. But we're gonna revisit them now, hopefully in a different light, so that they'll sink in better in your mind next time you think about them. We're gonna start with a discussion on standard deviation. And standard deviation, everybody has a colloquial understanding of standard deviation, but I wanted something different. So let's see how we're going to try to explain it in a different light. Consider some data, xi, yi, for example, the femur length or versus height data that we obtained, okay? Just to give a concrete example, and this is those data plotted in the plane, okay? Now, my question to you is, given a set of data, femur height, etc., what is this, in the absence of your knowledge of anything about those data? I just give you data. What is the simplest piece of information you could give about those data. I'll give you a hint here. So for example, assume that you want to set your dining out budget, okay, for next month. And assume that you know what you spent for dining out for the last 6 months, okay? What would you set for next month? Yes, okay, why? It's like the simplest, right? It is the simplest piece of information, most concise piece of information that you can give about a sample or a population or a collection of data, okay? The average, you're right, okay? So for this particular, okay, so we call it the average or the mean value. It's the simplest metric. It's even simpler than the median, okay? Because the calculation of the mean is much simpler than figuring out where the median is, okay? And numerically, this is given with an overbar, and it's simply you sum up all the values, all your dining out budgets for the last 6 months. You might have had 50, 15, 70, 33.5. You sum them up, divide by 6, and you get an average idea of your spending. Okay, so you sum up all the dependent variable values and divide them by the number of observations. For this problem, the height versus femur, it just so happens that the average height we get with those data is 167.8. Okay, so we draw that on a line like this. Okay, mean value. Great. Now, the mean value always divides the data between values above it and values below it. Not the median, this is the mean value. There are values that are higher than the mean and values that are lower than the mean. Now, each data point falls at a distance, call it yi minus y bar from the mean value. And it's that distance in purple here. So y bar is your mean, yi is your numerical value for each one of those observations. Okay? Now, don't think of this as an error, but that distance, that's a distance, okay? Just like we did before, what would be an aggregate measure of the average distance of all of those points from the mean? Pythagorean norm, right? So if you sum up the squares of all of those distances for all of these points, that gives you an average distance squared. Okay, so we haven't checked the units yet, but this gives you an average distance from the mean. How far on average are the data spread around the mean? Okay. Okay, great. So now we can compute. So that was the aggregate distance. Okay, so the units are still squared. Okay, yi squared, the units. So now how can you compute an actual average distance from the mean value? Okay, so go ahead and try to develop a formula. So that formula, so right now yi minus y bar squared, their summation is squared, right? I need to get rid of that square, but I also need an average distance, right? So you have n observations, okay? So think about how you would average that distance. So that's the aggregate distance. That's the total distance for all points. How would you obtain an average distance from the mean? What is the, on average, how far is the data away from the mean? So you clearly need to divide by something, which has to do with the number of data points. Okay, but you also need to adjust to get rid of that square. Okay. Okay, why'd you have n minus 1? Why do you have n? Did you want to do a sword fight? Okay, so I think you got it. Okay, some of you have square root of this summation over n. So this summation divided by n gives you an average of the square of the distance, right? You might think. And then you take the square root to make the dimensions correct. So you get square root of summation over n, correct? Who has n in the denominator and who has n minus 1? So who's got n in the denominator? Okay. Okay. So we got, okay. Who has n minus 1? Okay, those who have n minus 1, give me an explanation. Go ahead. You don't have some, okay. Okay, okay, that's correct. That's correct. Yeah, who's who did you, Nathan, did you have the n minus 1? No. N. Okay. Well, I would do n at first sight, right? But it's the n minus 1 that's correct, and we need to understand why. Who had the Rich? N minus 1 jumps. Okay. Who else? Okay, so yes, Gavin. No. But because we already, okay, so this n, you divide by n, it's not necessarily you're dividing by the number of data points you have. You are dividing by what we call the number of things that you don't know about your data. By your degrees of freedom, we call that. However, we already have 1 degree of freedom, which is the mean. Now, if you know the mean, and n minus 1 points, then you can deduce the last point. So really, because you know the mean, you've knocked out knowledge of 1 of the data points already. And that's why you have to do n minus 1. Now, for large data sets, it's not going to be an issue at all. Okay. But strictly speaking and rigorously, when you have a sample, when you're dealing with a sample, you need to divide by n minus 1 because you already know the mean, and the mean knocks out 1 degree of freedom because you already used the data to compute the mean. Now you're using the mean in the formula. Well, you've already knocked out 1 degree of freedom. Okay. So when you do this, this is the formula for the average distance from the mean. Okay, and I'm going to call this SY, and this is called the standard deviation of a sample. Okay, you've probably learned it this way. This is great. So we're revisiting this. But in my mind, the standard deviation is simply the average distance of the data on average. How far is the data away from the mean? The mean is very important because it is the simplest piece of information about some sample, about some data. We always hold it to the highest standard. We're going to do everything with respect to the mean. So the standard deviation is the distance from the mean. So when you think about, if you've done some statistics, when you think about the bell curve or the Gaussian distribution, right? You say, oh, 68% of the data falls in within 1 standard deviation. Okay, so that standard deviation is the average distance from the mean. Okay, most of the data fall within that distance. Okay. Okay, so for our case, and I need this number because as we pursue this analysis, we're gonna have to use this number. This is what this looks like. Okay, the mean, and you have standard deviation above the mean, which is 3.16 centimeters in this case, and 1 standard deviation below the mean. That's kind of what it looks like. Okay. And I define this as a measure of the spread of data around the mean value. Okay. And I already mentioned that for a normal distribution, you probably know this, 68% of the data fall within 1 standard deviation. So if these data were distributed normally, whatever that means to you, we're not going to talk about that. then 68% of your data falls within 1 standard deviation, and 95% falls within 2 standard deviations, okay? Now, in some cases, you will see n used in the denominator here, okay? And that is also true, but for a population, not a sample. So then we get into statistics and probability jargon. For a population, the standard deviation is a property of the population, not a statistic. So that's why you have to divide by n, because you kind of don't need the mean to compute that standard deviation, okay? Anyway, let's do this activity and then we move on. You can go. Okay, which one of these data has a larger standard deviation? This one? Yes, because the data is spread further away from the mean, okay? I will see you next Tuesday.